All right, welcome back. Now, let's do an example of using a logistic growth model, and we're going to use the California example that we used before when we modeled it using an exponential model. So let's say this is the model we're going to use, and this is the logistic growth model. Let's say the population of California is based on this growth model. Let's say the carrying capacity is 93.3 million, and this will be the denominator. So 1.5 e to the negative 0.0. Right, so there's our constant. So now what we're going to do is we're going to determine the population in 2010. Okay. Now we were told that the population in 2010 was what? 37.3 million. Let's see what this gives us. When we plug in 2010, right? So let's say 2010. Again, t was equal to 0 at that time. Let's see here. Okay, so now I'm going to put in, so let's try this. This is 0, right? So 0 represents 2010. So that means this becomes 1. So this will be, let's see if this is, if I'm doing this right. So 93.3. And then this is going to be 1 plus, since this is 0, this will become 1. So this will be 2.5, right? So we're going to divide 93.3 by 2.5. Oops, hold on. And look at that, we get 37.32, not bad. So in 2010, we got 37.32. So very accurate. So okay, good. Now it says determine the time required the population to double. All right, so now we're going to do the same thing we did before. We're going to find that time. Last time, if you recall, we got 2200. Let's see what we get now. So here, we want the population to be double. So again, 37.32. We're going to use this figure here, right? So that means it's going to be 74.64. So the population is 74.64 equals 93.3 over 1 plus 1.5 times e to the negative 0.013 t. Okay, now I'm going to divide, I'm going to multiply both sides by this denominator, and then I'm going to divide both sides by 74.64, right? So what I'm going to get is basically I'm exchanging both of these. So I'm going to get 1 plus 1.5 e to the negative 0.013 t, because all I'm doing is multiplying by this. And then I'm dividing both sides by this, right? Right? So I'm dividing both sides by this. So this is going to go away. This is going to go away here. So I'm going to get this on one side, right? And I'm dividing by 74.64 over here, right? So now I'm going to get 1 plus 1.5 times e to the negative 0.013 t. And then I'm going to get that equal to what? 93.3 divided by 74.64, okay? So again, just make sure you understand what I just did there. All I did was I multiplied both sides of the equation by this, and then divided both sides of the equation by 74.64, and this is what I got. Okay. Now what I'm going to do is I'm going to subtract 1 from both sides, right? So I'm going to subtract 1. So nope, I don't want to divide. So I'm going to subtract 1 from both sides, right? So that's going to get rid of that. And then what am I going to do? I'm going to divide both sides by 1.5. And so what do I get? I get e raised to the negative 0.013t is equal to what? This whole thing. Right? And now what I'm going to do is I'm going to end up taking the natural log of both sides because I want to get the t out. So I'm going to take the natural log to get rid of this e. So I'm going to take the natural log of both sides, right? So let's do that, okay? Let me just write it here. So I've got this. Okay, so now I'm going to take the natural log of both sides. Let's do it over here. So I'm going to take the natural log of e to the negative 0.013t is equal to the natural log of this entire thing. So I'm going to write it out. 93.3. Let me erase this because you've already got that in your notes, I hope. Okay. So the natural log of what? 93.3 divided by 74.64 minus 1. Oops, hold on. Let me do this. Okay, and this is all divided by 1.5, like that. Okay. Now, all right, so now that's what I got. Okay, so now this natural log cancels with this exponential e. So now the exponents come out. So this is going to be negative 0.013t, right, is equal to the natural log of this whole thing, which is 93.3 divided by 74.64 minus 1, all divided by 1.5. Okay, so there's that. And now I'm just going to divide both sides by the negative 0.013. So I'm going to divide this whole thing by negative 0.013. And now that's my t value. So that's time, right? So all of that is equal to t. Now I just have to stick this into the calculator again. Make sure you're careful about how you put it in the calculator so you get the correct answer. All right, here we go. So I'm going to take the natural log of 93.3 divided by 74.64 minus 1, right? And I'm going to divide that whole thing by 1.5. All right, cool. So I'm taking the natural log of this whole thing right now. Okay. Now I'm going to divide that by negative 0.013. And I get 137.8 years. So I get approximately 100 and what was it? 137.8 years. 137.8 years. Okay, I think that's what they asked. They said determine the time required. Right, okay, so now they didn't ask us for a year, they just said, hey, the time required for the population to double. So this is going to be approximately 138 years. So last time, if you remember, the last time it was 89 years to double. Okay, but using the logistic growth model, it's going to take much longer to get to the point where the population is double. Okay, and again, realize because as the population is growing, the growth rate tends to decrease. Okay, it's not a fixed growth rate like in the exponential model. The logistic model has a growth rate that changes.